Hi everyone, this is Team JoJo. The topic of our project is fast transfer learning for GAN style transfer. First, we have a GAN network trained to perform style transfer from real image to style A. Then we want to perform transfer learning to train a new network to transfer style from real image to style B. One common way of transfer learning is fine-tuning. It uses pre-trained weights as initialization and trained on the new dataset. But it is just a better initialization, does nothing else. Can we improve it by considering the model size, data, training time? Thus, our task is first to re-implement the cartoon GAN model provided in the paper, then perform effective transfer learning from higher style, which is style A, to hierarchy style, which is style B, using this network. And the goal is to achieve faster learning with less trainable parameters and less data. To achieve our goal, we first try naive fine-tuning techniques for our cartoon GAN models as a baseline reference. We use the model trained on higher style images as the initialization and train it on our hierarchy style dataset. Beyond that, we introduce meta-transfer learning. We will call it MTL for short. MTL was previously used on classification tasks. To fit the problem well, we separate this method into two parts, scaling and shifting, and generator decomposition. Scaling and shifting is quite intuitive. Instead of training the whole network from the pre-trained initialization, we can assume that style B weights are obtained by scaling and shifting the pre-trained weights. As shown in the picture, the parameters in the original data are frozen, and only the scaling and shifting parameters are being updated during the training progress. We can see that the method significantly reduces the learnable parameters and increases the training speed. The second part is decomposing the generator. This is the general structure of our generator. Intuitively, we can divide it into encoder part and decoder part. The encoder part should be able to extract low-level features of given images, like edges, points, and so on, so we expected it to keep almost the same given image in different styles. In order to further investigate the division between encoder and decoder, we have visualized the output of each convolutional layer for 4 different animation styles. This is our result. For example, this is the real image. As you can see, compared to the latter layers, the output of the shallow layer has a much similar result across different style images, which means it extracts style invariant features, so we choose it as the end of the encoder. This is the overall result of our project. We have largely reduced the number of parameters by 10 times. Also, we also make our model much faster to train. Here are some results from different styles. From the image, you can see a clear difference between the real image, the higher style images, and hierarchy style images. Higher is more red, hierarchy image has sharper edges. These two are from the baseline and MTL. Here is the result for comparing baseline and MTLs, which is our approach. MTL with fixed encoder produces similar quality as baseline, although baseline preserves more details. For example, the cheek here, here, and here. Also, MTL with fixed encoder produces better results than naive MTL, which is the one without fixed encoder. The naive MTL is more red, which is more like the higher style. Here are some field examples. The scaling and shifting restriction of weights seem to worsen GAN stability and cause mode collapse and artifacts. Here is an example of mode collapse. The generator sometimes turns the image into entirely black. Here are also some images of artifacts like overly yellow and changing color. To wrap up, MTL is a more effective transfer learning method on GAN style transfer network with less trainable parameters and faster learning, but it worsens some of the GAN's problem like mode collapse and artifacts. This is our presentation. Thank you for your watching.